So we're very glad to have Graham Manuell from the University of Coimbra today, talking about monoid extensions and the Grothendieck construction.
Okay, thank you. Yes, and I'll just say if anyone has any questions or anything while I'm talking, I know it's difficult over Zoom and everything, but you can interrupt me if you want to ask any questions or anything. That's perfectly fine. So I think let me just start by talking about group extensions, because maybe these will be a little more familiar to some people. So an extension of groups is essentially this short exact sequence that we have here. So we have a quotient of the group and the corresponding kernel. So if we have a group, it's of course very easy. We can consider these quotients and the corresponding normal subgroups. And these will always give us an extension of groups. But usually, what's slightly more interesting is if we fix the group that's going to be the kernel, and we fix the group that's going to be the quotient. And we ask, what things can we put in the middle? So what groups and what corresponding inclusions and surjections can we have such that this gives an extension of groups? And this problem has been completely solved. You can specify all of the possible extensions for a given group H and a given group N. In terms of this data, we have a map alpha, which acts a bit like an action. And we have a map chi from H cross H to N. And this is called a factor system. And they satisfy these conditions. They aren't necessarily group homomorphisms or anything. They just satisfy these axioms. And the precise axioms I've given here aren't important, really. Don't worry too much about all of the conditions. The point is that a characterization exists. And in fact, if there's anything you should worry about the conditions, is that they maybe don't seem super intuitive. It's maybe not clear what exactly these conditions mean, what the kind of motivation for them is. But the characterization does exist. But there is quite a natural way to understand where these conditions come from in terms of category theory. And that is that they arise as a special case of the Grothendieck construction. So I will explain this in more detail later in the talk. But the Grothendieck construction gives us correspondence between pseudofunctors from a category into cat and op-fibrations over that category. And I've written a co here in cat. So co, of course, means you reverse the two morphisms because cat is a two category. And it doesn't matter in this case. I could have just said into cat because it makes no difference here, but it will matter when we do some generalizations later. But this case for groups is quite well understood. So the question is, how can we extend this to understand certain classes of extensions of monoids? So group extensions work very well. In order for extensions of monoids to be better behaved, usually we restrict to certain subclasses of extensions of monoids, but they behave very similarly. So you have some quotient of the monoid, and then you have some kernel, and I mean here kernel in the sense of the elements of the monoid which are mapped to the identity. But there are certain classes, and we'll see that we'll arrive at these classes in a natural way through the process of the talk. And because general monoid extensions are not quite so well behaved. Okay. But before I start on kind of the main construction in the talk, I'm just going to, I think I'll first give some background ideas about category theory and how the monoids are fitting into this. So many people in the audience will probably be familiar of this idea that a monoid can be viewed as a one-object category. So we're just going to have a single object, which we'll call star, and then the morphisms of the monoids, or the elements of the monoid, will become morphisms in the category. And composition will just be the monoid multiplication. And then if we want to have a monoid homomorphism between two different monoids, these are going to be precisely the same thing as functors between the corresponding categories. Okay, so far so good. That's probably quite familiar. But maybe something which you might not have considered before is, what about the natural transformations? So if we have two monoids and we view them as one-object categories, and we have two monoid homomorphisms between them, we might ask, what does it mean to have a natural transformation between these functors? And well, a natural transformation is going to be a family of morphisms, and it's indexed by the objects, but there's only one object. So it'll just be a single morphism. And in this case, this will just be a single element of the monoid n. And it needs to satisfy a neutrality condition. And what this ends up meaning is that you've kind of got this commutativity type condition going on, where if you multiply on the, so you've got a single element t, and when you say t times f of m, that's always going to be the same as g of m times t. So that's just something that'll be useful to bear in mind as we go forwards. The next concept I'm going to need is that of a profunctor. So if a functor is kind of like the categorical version of a function, then a profunctor is like the categorical version of a relation. And for me, a profunctor from C to D is going to be a functor from C up cross D to set. Sometimes people use different conventions where they might go from D up cross C to set, or various other permutations, but this choice is going to be most convenient for us. Okay, so an important class of examples of profunctors will be those arising from functors. So whenever we have a functor from C to D, we can essentially compose it with so Hom itself will be a profunctor from D to itself. And that's in some sense the kind of canonical example. But then when we have any functor, we can obtain a profunctor by composing it with Hom. So in this way, a functor f from C to D will give us a profunctor, which we're calling hf from C to D. Okay, good. And it's useful, especially in this setting, to think, what does this mean in the case of monoids? So the case of one-object categories. And a functor from a one-object category to set is going to be the same as an M set. So the single object will give us a set, and then the morphisms, this being a functor, is going to give us an action of the monoid on that set. And for a profunctor from Bn to Bn, this is going to be what's called an Mn biset. So it's a set that has a left action by M and a right action by N. And there's this associativity or commutativity type condition that shows these actions are compatible. Okay, good. Now we can compose profunctors. And if you're familiar with coends, you can write this as a particular coend. And this is very analogous to composition of relations, where we've replaced the existential quantification in the composition of relations with the coend, and we've replaced the conjunction with a product. But we can also write out what this means explicitly. So we take a product of essentially the corresponding of like the profunctors applied to the various things, the input profunctors P and Q. And then we take a co-product of all the possible intermediate objects. And then we take this particular quotient where we identify things depending, so that if we act on the left-hand side of the pair with the one, using the one profunctor, this is the same as acting on the right-hand side using the other profunctor. And this will generalize functor composition. So it'll agree with the functor composition when the profunctor comes from functors. And so this allows us to compose the profunctors. We can also have two morphisms between profunctors, which are just the natural transformations between the underlying functors. And this will give us a bicategory of profunctors. So in case you don't know what a bicategory is, it's like a two category, but composition of one morphisms will only hold up to natural isomorphism. Okay. So again, we can now ask, what does composition of profunctors mean in the case of monoids? So we said that a profunctor between object categories is going to be this notion of a biset. And then there's a tensor product of bisets. And you can think of this like tensor product of R modules or R bimodules. But where instead of using as the base kind of construction the tensor product of the underlying abelian groups, you just use Cartesian product of the underlying sets. So it's just the Cartesian product, and we quotient out by the action, so that if you act on by M on the one side or on the other side, you kind of end up getting the same thing. And this is corresponding to our composition of profunctors. So we can think of the category, so we get a bicategory whose objects are monoids, whose one morphisms are bisets, and whose two morphisms are biset homomorphisms. And this can be identified with like a sub-bicategory of profunctors consisting just of the one object categories. Okay, good. So is everything reasonably clear so far? Okay. So one last thing of background, and this is the notion of a lax functor. So between categories, we have functors. Between two categories, you can, maybe the most obvious version of a map between two categories will do something to objects, one morphisms and two morphisms, and it will preserve composition and everything strictly. But slightly better is to preserve the composition, again, only up to some kind of coherent isomorphism. And for bicategories, this is really the correct notion. But we actually are going to want something slightly more general. So there's the notion of a lax functor between bicategories. And rather than having an isomorphism between the functor applied to a composite or the composite of the functors applied to the morphisms, we're just going to have a map between these. And they will satisfy certain coherence conditions. So just to say explicitly what this means, a lax functor between bicategory C and D, you need to say what it does on the objects. It'll just be a function. For every pair of objects, there will be a Hom category, and we must have a functor on between all of the Hom categories. And then rather than saying, okay, we must have that there's an isomorphism between the unit and L applied to the unit, we're just going to have some map, which isn't necessarily invertible. And these maps are called unitors. We'll have one for every object of C. And then to handle composition, we have something similar where we have these maps, which are, or these two morphisms, which we call compositors, which relate the composition. And these will need to satisfy a number of coherence conditions, but I don't think for the purposes of this talk, it's worth getting into the details there. Good. So now it's time to talk about the kind of main construction that we will use in this talk. So the kind of the core construction that we will make use of. And this can be kind of motivated as follows. So suppose you have an arbitrary functor between categories. And you might ask, what is a notion of a fiber of this function? So a fiber of the function, I mean in the sense of a fiber being like a preimage of a one object set for a function. And so we can ask, okay, for any object in the codomain, we can take the set of objects which map to that object. So if the object's D, it's the set of objects which map to it. And we can also consider the set of morphisms which map to the identity on D. And this will be a certain subcategory of C, which it makes sense to understand as being the fiber of the object D. But now we might also want to know, okay, so for every object, we get this fiber category. But what happens, how do morphisms in the codomain category relate to these fibers? So how do fibers vary along the morphisms? And one very natural thing to consider here is we can think, okay, before we've considered all the morphisms which get mapped to the identity, what happens if we consider the morphisms which get mapped to a given other morphism, F? And this suggests the following construction. So we can consider for every object A bar that capital F maps to A, and for every object B bar that capital F maps to B, we can consider all the maps F bar from A bar to B bar, such that capital F maps F bar to F. So this is a natural construction. And essentially, by considering composition on the left and on the right, we can make this into a profunctor. So this object, which I'm writing as partial F, this is going to give some kind of map from the category D into profunctors. And it turns out what it'll give is it'll precisely give a lax functor from D into profunctors. So D is just a one category, but we can view it as a two category in the kind of trivial way by only having identity two cells. So I've told you what it does to objects and what it does to morphisms. But in order to give the data of a lax functor, I also need to tell you what the unitors and the compositors are. So the case of the unitors is quite easy. Just from the construction, we can see that when we apply partial F to the identity morphism, it's just going to give the entire Hom profunctor. And I should have mentioned this before, but Hom sets provide the identity profunctor and a profunctor composition. So we have that F maps the identity to the identity. So it makes sense that we can just take the unitors to be the identity two morphisms. And in general, any lax functor where the unitors are just identity two morphisms is called a normal lax functor. Okay. But now we need to worry about the compositors. And this is slightly more complicated because it involves the profunctor composition. But when you work out what happens, remember profunctor composition can be understood as these equivalence classes of pairs. And if you have a pair which is F bar comma G, all you need to do is you need to map it to the composite F bar G bar. And this takes something in, so if F bar is something which F maps to little f, and if G bar is something that F maps to little g, then their composite will be something that F maps to Fg. So this kind of makes sense. And indeed, it turns out that this does give us the notion of a lax functor. Okay. again, I hope all of this is clear so far. If there's anything you want me to say in more detail, just tell me. Okay. So here we have a construction, a fairly natural way to consider the fibers of a functor f, and then get this normal lax functor into profunctors. And we now might ask, can we recover f from this fiber construction? So just from the fibers, can we recover our original functor? And it turns out we can. And in fact, if we have any normal lax functor, we'll be able to construct any normal lax functor from D. I say D op here, that's a mistake. Ignore the op. So you have any normal lax functor from D into prof. And we are imagining this to be of the form partial f, and we want to recover f. So this is going to somehow involve, so if at every object, f is going to give us the fiber of that, at that object. So the entire domain category will be obtained by essentially, in some sense, some kind of disjoint union of all these different fibers. So we somehow need to glue these fibers together in order to get the domain category. And after that, we can worry about constructing the actual functor f. So that's what we're going to do first. We're going to look at this category. And I'm calling this category integral of L. And the objects of this category are going to be pairs. So firstly, it's going to be an object in the category D. And then it's going to be an object D bar or an object D bar, where D bar is viewed as being an object in the fiber of D. So L of D is a category because the objects in prof are categories. So it makes sense to consider an object D bar in L of D. Okay, so that's the objects. Morphisms are similar. A morphism is going to be given by a pair of, and where the first component of the pair is a morphism in the category D. And again, from our fiber construction, we know that in that case, the elements of the profunctors are going to give us essentially going to give us morphisms in this codomain category C. So the second component of the pair will be an element of LF applied to D bar and E bar. So it'll be an element of this set obtained from the profunctor. And then I need to tell you how to compose things. The first components compose easily. The second components, we use the compositor, which again, in the case when we worked at what the fibers were, you might recall that just took composition. So it's exactly what we need here in order to construct the composition of two morphisms. So we just apply this compositor map. And then I also need to tell you what the units are. And here we use that this is a normal lax profunctor. A normal lax functor. And so L applied to the identity is just going to be a Hom set. So it makes sense to consider a morphism in the second component, ID of D bar. So we can just have the pair of the identities, and these will act as the identities in this category. Okay, good. So this is a generalization of what is normally called the Grothendieck construction. We also need to define a functor. So I've told you how to get the category C, but it turns out that the functor is now very easy to describe. All we do is we send the pairs D comma D bar to just the first component, D, and similarly for the morphisms. And these two maps, this map partial and this integration operation, are given actually an equivalence between the functors mapping into D and the normal lax functors from D into prof. Though I write an asterisk on the slide here because the second bicategory, the one morphisms are maybe not exactly what you'd first expect, though they are quite natural. But we aren't really going to need to consider them on this talk, so I won't get into the details about that.
And when you write slice to category, is that like a strict sort of slice?
Yes, it turns out I think that it doesn't really matter whether it's a strict slice or whether it's up to whether you have an isomorphism there. But because I think they're equivalent. But yes, it's you can think of it as a strict slice category. It's not lax or anything like that. Okay. Good. So I hope this construction is more or less clear, because it's really what we're going to be using now for the rest of the talk in order to understand these extensions of monoids. But before we move on to monoids just yet, I do want to talk about a restriction of this construction, which, if you're familiar with the usual Grothendieck construction, might make things look a little bit more familiar. So I've said arbitrary functors are going to correspond to these normal lax functors into prof. But we know that if you have a functor, this will give us a profunctor. So we can think of the two category of categories as being a sub-bicategory of the bicategory of profunctors, where we don't consider all profunctors, but only ones that are obtained from functors by this map H, which I mentioned before. And now we can ask, okay, which functors correspond to the normal lax functors which factor through this inclusion? It's actually an inclusion of cat co into prof, because the direction of the natural transformations ends up being reversed because we're putting the functor in the contravariant part of the Hom functor. But this is just a minor detail. But essentially, we can ask which lax functors end up factoring through cat, or factoring through cat co, and what functors do these correspond to under this construction? So, well, what this means is it means that the profunctors we get are of the form of some functor, as we kind of talked about before when we are saying how functors give rise to profunctors. And so we're going to have this natural isomorphism between partial f of f and this Hom involving some functor, which I'm calling f lower star. And remember that what partial f is supposed to be is it's supposed to in some ways the profunctor is supposed to describe the morphisms f bar which map to f. And what this natural isomorphism is saying is that these are going to be in bijection with certain morphisms from f star of a bar to b bar. So if you think of this kind of in terms of the Monoid lemma, the idea is that there's a universal map from a bar into f star of a bar. And composition with this universal map is going to be how we relate these morphisms from f star of a bar to b and the morphisms from a bar to b bar. And if we just write out what the universal property of the map is, we're going to see that it has this following property, which is called op-Cartesian. So we say an arbitrary morphism U in a category C is op-Cartesian with respect to the functor f, if whenever you have any, pre-op-Cartesian, if whenever you have any morphism G bar from A bar to B bar prime in C, and this morphism G bar maps to the same thing as U. So they kind of lie in the same fiber. Then there exists a unique map, B, which maps to the identity on B. It maps to the identity on F of B bar. And there's this unique map such that when you compose B and U, you get G bar. So this is exactly what the universal property we got for U above is, and we're just giving a definition to it. And we'll say that F is a pre-op fibration if for every morphism from F of A bar to B, there exists a pre-op Cartesian lifting UF. So then UF is going to be mapped to F under capital F. And also the domain of UF is going to be A bar. If you've seen the definition of an op fibration before and you wonder what the distinction is, it's to do with, well, either you can formulate the universal property for an op Cartesian map as a slightly stronger condition, or you require that they compose. But we won't need to worry about this for this talk. But okay, so we see that this condition always holds in the case that we factor through cat. And what this allows us to conclude in a fairly simple way from the more general construction mentioned before is that normal lax functors from D into cat co correspond to pre-op fibrations over D. And just in case that was all very hard to follow, maybe the diagram here will make things a little bit clearer. The point is that so at the top of the slide, we're going to have the category C, and at the bottom of the slide, we have the category D. And F essentially maps things vertically to the corresponding place. So B bar and B bar prime both map to B, and A bar maps to F of A bar, and UF maps to F. And whenever we have any other map G bar, there's this unique B which maps to the identity such that the diagram commutes. So this is what the condition gives. And it just arose in a very natural way by considering this isomorphism of these certain Hom sets. Okay, good.
Can I just ask, actually, if you restrict the bijection between the pre-op fibrations and the normal lax functors, if you restrict to normal pseudofunctors, does that capture the pre-op Cartesian morphisms being closed under composition?
Yes.
Or something like that?
Yes, so the way to kind of think about it is that if you have we've got a lax functor, so things don't compose properly. We just get a morphism from the composite to the other things because lax functors don't actually preserve composition. But if we had a pseudofunctor, then you do end up preserving composition in a more reasonable sense. So pseudofunctors are going to correspond to the case where you have a proper op fibration, not just a pre-op fibration.
Thanks.
Good. So now we can finally see how we can apply this construction to monoids. So a natural question to ask is, if we have a monoid homomorphism, we've now seen that these pre-op fibrations are maybe important in some way. When is the corresponding functor corresponding to this monoid homomorphism? When is this corresponding functor a pre-op fibration? And we can just rewrite the definition, essentially just in terms of the monoids. So we now say whenever there's an element of H, then there's some kind of lifting UH in the fiber of H, such that whenever you have anything else in the fiber, there's a unique N in the fiber of the identity, such that NUH equals G. Notice in particular, for every element H in big H, there is something in its fiber. So in particular, the map E is surjective. And now this pre-image of the identity, we can take this to be this is of course a monoid, N. So this is the kernel of the map E. So because E is surjective and we now get this kernel, this gives rise to an extension of monoids. And it's not just any extension of monoids because it satisfies this condition, which I've just written on the slide. But it turns out this condition is a well-known condition for extensions of monoids. So this is precisely the condition for this extension to be what's known as a Schreier extension of monoids. So this has already been studied, not necessarily, well, independently of them being pre-op fibrations or anything. These extensions are an important class of extensions of monoids. So just by asking when a monoid homomorphism is a pre-op fibration, we've recovered this known class of extensions. Okay. But of course, the construction allows us to relate pre-op fibrations to these normal lax functors into cat. So let's see what this correspondence means in this case. Now, of course, an arbitrary pre-op fibration into the one object category BH could map from a general category. So an arbitrary pre-op fibration isn't going to be a map between one object categories. In this case, it will be a map between an arbitrary category and a one object category. So we want to restrict it to just be a map from a one object category. And then ask, what does this restriction mean on the other side? Well, we know that essentially partial E at the unique object is going to be the fiber. So this is going to correspond to N, which is itself a one object category. So in this way, we can see that if we just want to restrict the monoids everywhere, the Schreier extensions with co-kernel H are going to correspond to normal lax functors from BH into what I'm calling mon-co. So mon is the two category of one object categories, or alternatively, it's the two category whose objects are monoids, whose morphisms are monoid homomorphisms, and whose two morphisms are those elements of the monoid satisfying that condition, which I mentioned before. And of course, as I've kind of mentioned, what this normal lax functor does, it's going to send the single object to the kernel of the extension. Okay, good. So that's what our correspondence gave us in this case. So we can now try and unravel all of these definitions of lax functor and so on in order to obtain an explicit characterization for these Schreier extensions of monoids. So let's do this. So we need to understand what a normal lax functor from BH into mon-co gives. What is the data? So remember from the definition of a lax functor that we need to say what happens to objects. In this case, there's only a single object in the domain. So it's just going to give us a single object in the codomain. So that'll just be a single monoid. And we also know that it's going to be the fiber N. Sorry, the kernel N. Then next we need a functor. There's only one object, so we've just got a single hom category to consider. So we have a functor which is going to map from H to mon of L of star to L of star. So this is the hom set or the hom category in the category mon. And in this case, though, there are no non-trivial 2 cells. So we can just think of it as a function from H into these kind of monoid endomorphisms. So we have a function from H to the monoid endomorphisms of N. And actually, we can rewrite this in terms of something which looks more like an action. So for every H, we have a map from N to N. We can write this as a map alpha from H cross N to N. And then the fact that it needs to be a monoid homomorphism, we can just express as these conditions. Next, because it's a normal lax functor, it means that when we apply alpha to the identity, it should just be the identity map, or more explicitly, alpha of 1 comma n as n. And then finally, we have these two morphisms for the compositors. And we need them for every pair of elements, H and H prime. And this is in mon-co, so we're going to need to reverse direction if we're working in mon. So if we substitute in what we had for L in terms of alpha, this is going to be a monoid 2 morphism from alpha of HH prime, comma blank, to then this composite of alpha of H and alpha of H. And again, unraveling what it means, what a 2 morphism for monoids means. Well, we're going to need something for every H and H prime. So we might as well call this chi of H comma H prime. And this will be an element of N. And then it needs to satisfy this condition where you multiply chi on the left on the one side and chi on the right on the other side. And there were also these coherence conditions, which I omitted, but they give 2 extra conditions. But now all of these conditions, if you look at them, what we've got, they will look very similar to the conditions I gave on the first slide for group extensions. And indeed, this is the usual data, which is known for classifying Schreier extensions of monoids. But now we've obtained it in a very kind of natural way through this categorical construction. So this gives us some idea of where these conditions have come from. Again, it requires quite abstract machinery, but nothing is really difficult. There wasn't really any step which required a large amount of creativity or anything. As long as you just worked with the lax functors in the appropriate way, we just very naturally were able to derive this characterization. The characterization has been known before, but it was described in quite an ad hoc manner. It wasn't really clear where all of the conditions came and what they meant. Okay, so this is the data, but I haven't actually told you how to go from the data to an extension. But of course, the Grothendieck construction which we described is exactly what you need to do this. So remember, we need to construct this category, which we write with an integral, and then the lax functor is going to correspond to this profunctor, or this. I'm kind of abusing notation. I'm realizing maybe by calling this HL, because HL is usually what we do for the profunctors rather than for the things that map into profunctor. But I hope you kind of understand what I mean by it. It's just we're composing L with the inclusion into profunctors. And the idea is that we know that when we do this construction, we're going to use pairs of objects. Well, there's only one object, so we just get a single object in this resulting category. And we use pairs of morphisms, where the first morphism is going to come from the domain category of BH. So that'll just be an element H of big H. And then the second morphism, of course, we need to apply the profunctor in the appropriate way. But again, there's just a single object, and we know that this profunctor comes from a functor. So the result that we get is it's always just going to be n. So it'll always be the same thing. So we end up getting these pairs where the first component comes from H and the second component comes from N. And then we can again see what our construction gave for the multiplication. In the first component, we just multiply normally. In the second component, we need to apply this compositor to this certain equivalence class of pairs. Now, to make sense of this, this equivalence class of pairs, we can either think of it in terms of profunctor composition, or because we're dealing with monoids now, we can think of it in terms of tensor product of bisets. But what the conditions for those mean is that we can move things between the components if we are by using the actions. So it turns out that if you think of the right-hand side of being n prime times 1, then you can move it to the other side, picking up an action by L. And then you need to apply the compositor to this. And when you unravel all the details, you get the following. So you multiply the first components. For the second components, you multiply n, but by n prime, but acted on by this action. And then you use the data given by the compositor. So this will give us our central monoid in the extension. And then, of course, we can also obtain the relevant morphisms just by projecting onto H. This will give us the surge action, and then, of course, take its kernel to get the kernel map in the extension. And this construction, this multiplication, this might remind you of, for example, semi-direct product of groups. That will be similar to this, except we won't have this chi. That will be trivial in this case. Or maybe it will remind you of the characterization of extensions of abelian groups, where you don't have the action, but you just have the chi. So, but this is, again, we've recovered the known construction for the characterization of the Schreier extensions of monoids. Okay, good. So I hope that's reasonably clear. I now quickly just want to talk about a slight generalization of this. So this is maybe the most straightforward approach to take. And Schreier extensions are really one of the more important classes of monoid extensions. But there's a more general class, which is very general and includes almost all of the classes of monoid extensions that are studied, at least monoid extensions of this particular type. And this is this idea of weakly Schreier extensions. And the definition of a weakly Schreier extension is very similar to the definition of a Schreier extension, but we remove the uniqueness condition on the element n in the kernel. So it's exactly the same, but without the uniqueness condition. And now we might ask, okay, can we generalize these in a similar way? Does the approach still work? And it does, but we need to introduce some new notions. So before we had this notion of a pre-op Cartesian morphism, now we will introduce the notion of a weakly pre-op Cartesian morphism, which is exactly the same, but with the uniqueness condition on B relaxed. And again, this gives rise to a weak pre-op fibration. Okay, so exactly the same as the previous definitions, but without the uniqueness in the particular place. And now we might ask, okay, so what do these correspond to? We know that the pre-op fibrations correspond to maps that factor through cat. What about which normal lax functors correspond to weak pre-op fibrations? And in this case, rather than being isomorphic to this particular HOM, we don't get as isomorphic because we don't get uniqueness. Because we only have existence, we just get that there's a surge action, not an isomorphism. So, and now this map F star of A bar, you shouldn't really think of it as a functor necessarily anymore. It's just the name I'm using for a particular object. So there's some object, and this is going to be a quotient of that particular HOM. And this will be natural in B bar, but as I say, F star is not necessarily a functor. So it's not, it doesn't make sense to say it's natural in A bar. So what does this condition actually end up meaning? Well, remember, I said that a profunctor from C to D is a map from C up cross D to set. So if we use the exponential adjunction in the category of categories, we can say this is the same as mapping from C up to set to the D. So where set to the D is this functor category of functors from D to set. And what this condition is saying is that for every object C in the category C, that this P hat is going to map C to a quotient of a representable functor. So that's what we've essentially derived above. So it sends it to quotients of representable functors. And you can show that this actually gives a sub-bicategory of prof. And these are the things which correspond to our weak pre-op fibrations. Again, you can now see what this does for in the case of monoids. So we know profunctors correspond to certain bisets. Well, if we want to know what the representable functor corresponds to as a biset, it's just going to be M itself, or rather, the representable functor as an M set. It's just going to be the left M set structure on M itself, where the action is just given by multiplication in M. So we need a quotient of these. So this is going to be some quotient of this particular left M set. So this corresponds to giving a left M set congruence on the monoid M. Then we also need the action on the other side by N, and this is unconstrained, except that it needs to satisfy this associativity condition with the action of M. So when you work out what this condition means, we can see that the action by N is completely determined by where the action of N sends this equivalence class of 1 in the quotient. And this map, so it's a map from N into this quotient of M. But we can think of it as maybe being a map from N into M itself. And then the requirements we end up getting for requiring that this associativity condition holds is that it mustn't necessarily be a monoid homomorphism, but it must preserve the unit and the monoid multiplication up to this equivalence relation. So we've got this M set congruence, and we ask that it doesn't necessarily send the unit to the unit, but it must send something equivalent to it, something equivalent to the unit. And similarly for the composition. So in summary, what we get is we have that the particular bisets that correspond to these weak pre-op fibrations can be described by a left M set congruence on N, together with this map from N to M, which is kind of almost a monoid homomorphism. Okay. So again, we can do the same thing we did for Schreier extensions, for the weakly Schreier extensions, and see what data we get. It's going to be slightly more complicated, but it's very similar. It's just wherever we had a monoid homomorphism before, we now have an extra equivalence relation, and the monoid homomorphism condition is weakened to be an almost monoid homomorphism with respect to these equivalence relations. So I've just given you the data here. Again, it's not terribly important what it is. The point is we can obtain it in a natural way, and this recovers the known characterization of weakly Schreier extensions. Again, we can do the construction. Given this data, we can work out what the corresponding extension is. In this case, it's slightly more interesting because rather than just having an element from H and an element from N, we have these pairs, but they kind of some kind of dependent sum, where the second component, exactly which equivalence relation we're taking, depends on the first component. And then the monoid multiplication is very similar. And as I say, it agrees with the usual construction. And I just want to end the talk by saying what more we can do with this approach. So as we kind of brought up with the question that John asked before, was essentially what happens if we deal with pseudofunctors. And you can ask essentially something even slightly stronger than that, where there's this notion of a fibration where the fibers are all groupoids. And there's a very natural correspondence between these certain kinds of fibrations and these certain pseudofunctors. And this will allow us to give an interesting characterization of when Schreier extensions have group kernel. Again, variants of this approach very easily give a characterization of what are known as Schreier split extensions or weakly Schreier split extensions. This is more directly analogous to the case of semi-direct product of groups. Because we had this entire equivalence between these categories of op fibrations and these categories, or in general, these categories of functors and these normal lax functors, it can also be used to characterize morphisms of extensions. And I've just shown how to do this for weakly Schreier split extensions, but I think it's plausible that other classes of extensions will also be able to be handled by this approach. But yes, that's all I had to say. So thanks.
Thanks very much. Any questions from anyone? Yeah, go ahead.
Yeah, thanks for the talk. It was very fun. So you started out motivating the monoid case that you managed here by the group case, right? The group extensions, and you motivated it by explaining that group extensions can be described by this set of equations, right?
Yes.
In the beginning, and then you moved on to monoids and did the stuff with the Grothendieck construction. So to then characterize a specific kind of monoid extensions, which are these Schreier extensions or certain variations of that. So if you play the same game with, you start with a group and then you look at an indexed group over that group with, I suppose, normal pseudofunctors, you end up with all group extensions or also a certain kind of subclass of group extensions, which are whatever Schreier, I don't know what that is.
Yes, thank you. That's a good question. I should have made this more clear. But it turns out that in the case of groups, all group extensions are Schreier in the monoid sense. It turns out that if you have a group homomorphism and you ask, when is this group homomorphism a fibration or an opfibration or a pre-opfibration, it turns out they're all equivalent. And it's precisely when it's a surjective group homomorphism. So in the case of groups, every group extension of groups is always Schreier automatically. In the monoid case, though, you get these extra extensions which are possibly badly behaved, and we only get the Schreier extensions from our construction. But this is really a Schreier extensions, generalized group extensions, in the sense that every group extension will always satisfy the Schreier condition automatically.
Yeah, great, thanks.
Any more comments or questions? Well, if not, then let's thank the speaker again. Yeah. So thanks very much for the...
There's something in the chat.
There's something in the chat. I'm not sure if it's a raised hand or a sort of applause. Let's see. Can you share your slides in this
yes,
chat?
I imagine, can I just send them to you and you put them somewhere?
Yeah, so I can put them on the web page if you send them to me.
Okay, well then I'll do that.
All right, thanks a lot. So stop recording.